I think it's better to run, got the report. Update the libraries also. Conda update WF and all. You update it and then restart the kernel. If you are doing in Jupyter Notebook or if you are doing in Anaconda prompt, you can close the prompt and restart the kernel. Once you have updated the libraries, see here, kernel, restart and run out. Once all the update libraries are updated, in Jupyter Notebook, you will get the number. If the star is there, that means it's still running. If you get the number, then immediately restart and run out. So if you are looking at the report, it gives a detailed report. See, overview. 25 variables, categorical 25, number of observations 12684, missing cells 0, duplicate rows 74, total size is this one. And then you can see the variables. Each variable's destination, correlations between the variables, missing values, sample, duplicate row. Acha, SciPy, it is not able to calculate the data actually, because some error. Actually, you'll get the data also. Sample, first rows, last rows. Variables, you should get the variable data here. I don't know why it is not coming. You'll get the report, mean, median, all those things. Correlations are automatically generated. See, Pearson's are Kendall's, these are all correlations. Here, we should get the variable report. That we are not getting. We are trying to do any other things. Or let us say, Pandas profiling report. Okay, variables, correlation height. Each variable, now we are getting it. See the frequencies and all. So you can click on toggle details and you will get the various options. This is the one we have to use. To notebook iframe. So when you use to notebook iframe, for each variable, it is giving distinct 5 categories. See the frequency count of the 5 categories. 1, 2, 3, 4 to 8, less 1, greater than it, and then the frequency counts. So this is one of the important library when you are dealing with large scale data. You can use Pandas profiling. Report of variables. How many missing percentages? What is the size? All that information you will get it using Pandas profiling. Earlier, I used to do a for loop to print all the frequency counts. Here, we are getting using one single function. So we can use anything. Any data frame you can pass. So first, after importing the report, we found out there are missing values. So we have dropped the column called car, which has too many missing values. Then we have find out the missing value columns, and we have imputed with most frequent imputation. We have imputed with the most frequent. Okay. Then we understood the variables using Pandas profile. So 2 coupon, GQ15, all are numeric, which are showing as integer. They are all 0 and 1. 0 and 1. GQ 25 minutes, 0 and 1. Direction same, 0 and 1. Direction opposite is again 0 and 1. So these are all what we call categorical data. And our dependent variable Y, which is coupon recommendation yes or no. One is 7210 5474. If you go to the data dictionary, you will see what does that 0 and 1 means. So in the data dictionary, so whether the coupon is accepted. 1 means accepted, 0 means not accepted. Whether, see, while traveling in the car, as they reach the Amazon store area within a particular kilometer radius, Amazon is sending coupon recommendations to the mobile app. If the customer has installed Amazon app and notifications are activated, they will get immediately notifications on their mobile regarding the coupons and offers, so that the customer can take a detour to the nearest Amazon store and use that coupons to buy. This experiment was done in Australia. In Australia, they have done this in vehicle coupon recommendation. Some people, what is happening is the mobile phones are tied up to the car audio system and all, right? So the notifications will be automatically displayed on the car or audio system or whatever system, Wi-Fi system or the GPS system will automatically display the notification. So once the product or the coupon recommendations are taken into, customer accepts the coupon, he will drive to that nearest Amazon store and use that coupon for executing transaction. So 7,210 customers have accepted the coupons. 5,474 did not accept the coupons. Coupons accepted means they have executed a transaction on the. So this is the data of Amazon trying out in-vehicle coupon recommendation in Australia. So this is our dependent variable Y. Dependent variable is, like I said, we have already understood the descriptive stats for each variable using the profiling report. Okay, missing values, all those things we have understood, and we have cleaned up the missing values also. Right. Now let us do some hypothesis. Test null, no association, y and gender. Y and gender, I think this is marital status. Hey, we have to remove this 2 coupon GUQ 5 min also. See, 2 coupon GUQ 5 min, it has only one single thing. In the report, you can see here, right? It automatically, the report is automatically saying you have to remove this because there is only one single value column. Remember, the whole column is all about 1, 1, 1. So you have to remove this variable 2 coupon GUQ 5 minute. So do these 3 hypothesis tests. What is the null? No association. So we are rejecting the null. That means there is a relationship between gender and coupon acceptance. There is a relationship between gender and coupon acceptance. So first do the cross tabulation, then the test. The second value in the output is the p-value. What is null hypothesis? That we are rejecting. We are rejecting the statement that there is no association between both variables. That means there is a relationship. The statement says no association or no relationship. That means there is a relationship between both the variables. That means gender is a variable that is affecting the dependent variable. So if you want to find correlation between categorical variables, Kramer's V is there, na? That is what is used in statistics to find correlation between categorical variables. For numeric variables, we do correlation and covariance. But for categoricals, they are categories, na? 0, 1, 2, 0, 1, like that. So Kramer's V is what is used for finding correlation between categorical variables. Even phi coefficient is also for categorical variables. Kramer's V is for categorical variables. Even chi-square test of independence also will tell us the relationship, right? Chi-square test of independence also is telling us the relationship between 2 categorical variables. Apart from chi-square test, we won't use any other test. We have to use Kramer's V. Kramer's V is another test because in one of the interviews they asked, one of the student called me last week asking what is the alternative for chi-square test of independence, which is nothing but relationship between 2 categorical variables. Kramer's V is the answer. So Kramer's V will tell you how strongly 2 categorical variables are associated. Kramer's V. Okay. In profiling report, we are getting that Kramer's V. And that fills this also. Fills theta also is for categorical variable. So you can see here Kramer's V. Now there is a very dark correlation between GEQ 5 min, we are anyway deleting it. The only problem is GEQ 5 min, which is black. Black means very strong correlation, right? And rest of all, I think, are moderate correlations on it. If you look at the color, there is no dark black. There is no dark black. Other than the diagonals, you don't see any dark black, right? There is one here, which is direction same and direction opposite. Direction same and direction opposite are also, direction same and direction opposite are also highly correlated. You can see that black thing, right? Strong correlation. Black is here. Black is strong, multicollinearity. So we have to delete GEQ 5 min and we have to delete either destination opposite or destination. And I don't see anything other, any other variable having any problem. Or we have one more black here. What is this black? This black is for same. Decision opposite, direction opposite and direction. We are worried about the blacks. In this anything light blue, little bit dark blue also, it is 80%. See here, we have some dark this, but this is around 80% only, not above 95%. Above 95% will be black, 0.95, not 95%, above 0.95. So alternative for chi-square test is Kramer's V and fills theta also, fills this one also, fill, what do you call it? One second. The formula is this. If you are looking at formula, the Kramer's V formula is based on Nij minus Nij by n into, this is the formula, taking the root of the chi-square statistic divided by the sample size and minimum dimension minus 1. And phi coefficient is also other measures. Phi coefficient. So we are getting in Panda's profile report both Kramer's V and phi coefficient. So Kramer's V is the alternative for chi-square test of distribution. It uses the chi-square output only. It uses the chi-square output only to calculate the correlation or Kramer's V, association between 2 nominal variables. Any n number of, that is n, na? In the formula you see n, right? K and parameters and also it is more than 2. Now let us drop those unwanted variables is equal to coupon recommend open bracket dot drop open bracket square bracket single quote to GEQ 5 minutes, and also we will drop one of them, direction opposite or direction same. Inference will be same. Direction same. I am repeating. Why we are dropping this? Multicollinearity. Multicollinearity. No, one is multicollinearity. The other is single value column. 2 GEQ 5 is the column is all ones. Multicollinearity is direction same and direction one. Opposite. So one column we are deleting because it's a single value column. The other column we are deleting because of multicollinearity. Now we will label encode all the data except temperature. You have to label encode all the other except temperature, right? We don't have any ID column, right? No ID column is there. So only thing is we have to not label encode temperature. Rest of the variables we have to label encode. sklearn dot preprocessing import label elite is equal to label encoder underscore encode is equal to coupon recommend dot drop temperature comma axis is equal to 1 dot apply le dot fit underscore transform. Y also has to be label encoded, right? But it will not treat it as categories until you label encode it. Until you label encode it, it will not treat it as 0 and 1. It will not treat it as categorical. See, the dependent variable has to be binary. If it is in 0, 1, it will be considered as numeric. If you try to do logistic regression, if y is int 64, will it run? It will simply say numeric dependent variable found. So what you have to do? Go back and label encode but why you should do that there? When you are doing label encoding for all other variables, do it along with y. Anyway, we have to encode y, right? Y has to be encoded at any point of time, right? So if you have CR is equal to PD dot read underscore, or let us say, oh, it is taking, even if you don't label encode y, it is taking. Maybe in the recent versions they changed it, but earlier we used to encode y also.
So when we use logic credit there, when we use logic credit,
because we don't give y there, it is only x. So even if you don't label encode y, but before that we need to add one more step. Coupon recommend df is equal to pd dot concat square bracket coupon recommend dot temperature comma object calls underscore encode is equal to 1. Because temperature we have removed, x is equal to coupon recommend df. Yes, 62.94. Even if we add temperature, I think now if it is binary, it is automatically taken. So we don't have now. We have dropped it here in object encode. If you didn't drop it here, you have to drop it from x. But I've dropped it here, right? So object encode doesn't have two columns, temperature and y. Remaining columns it is encoding. Now I'm adding temperature here. I am adding y here. So we have dropped those two variables, temperature and y, and then we have done the label encoding on the remaining variable. Now, when I'm concatenating, I'm adding the independent variable temperature. And anyway, y we need to show it separately. Y has to be separate. So y I'm calling it separately as coupon recommend dot y. And x I'm taking as coupon recommend df. If it is repeating, you will not get the model. It will say duplicate columns found. If there is duplicate columns, it will immediately say duplicate columns found. Dot fit dot score. Okay, all of you done with this? Build decision tree classifier. Because logistic regression is underfitting, right? What is the range for accuracy? 0.70 to 0. Logistic is giving 0.62. That means it is underfitting. So now we have to go to the next model, which is decision tree classifier. And then logic predict print classification report also. So from sklearn dot metrics classification report y comma logic. See here minority class there is some 0 class there is some sort of problem in prediction. Even majority class also not that great, right? Now we can go with accuracy and always by habit also look at precision recall and F1 score also. That you start even ROC also you should look at it. But the problem here is it's underfitting. Once it underfits, you can ignore other things. But when it is in normal range, you have to print classification report. You also have to print the ROC curve, what we call receiver's operating curve. That also you have to print to finalize which model. Then you build the next model and all. No? To finalize your best fit model, you have to have multiple metrics.
Sir,
Same 0.70 to 0.95. Closer to 1 means it is again overfitting. Let us see if decision tree gives it or not. From because there is not much of an imbalance. It is not big imbalance, right? What is the 10 percentage? If you look at it, if you look at our profile report, it gives us a thing. It is not that big. 7210 and 5414. If you click on toggle details, you will get the other ones. Frequency 56.8 and 43.2. If you click on the toggle details, for that you will get this thing. Now it's not an imbalance, right? Imbalance is what once you have 190%, the other 10%. But this is not imbalance. This is almost close to one another. What you call 10-13% difference is there. So it's not a big imbalance problem. Because of the categorical variables. Now, see in logistic regression, in regression by default, linear regression, logistic regression prefers more of numeric variables. Okay, they don't work if majority of the variables are categorical in nature. Like in the current data, only one numeric variable is right? Rest of all are categorical. So that problem will be there in binary logistic regression and multiple linear regression because they prefer numerical continuous variables and some categorical variables. If the complete data 99% is categorical and 1% is numerical, then the performance comes under. So the baseline algorithms will not give you that much of it. Length is just showing you the number of the first 5 and last 5. 99.81. 99. There is significant reduction in. Now, if you want to correct this problem, max depth is equal to 10. We'll start with 10. 79 and 65. This is closer. 79 and 65. 79 is slightly above our range, preferred range of 0.70. If you say max depth 8, max depth is 86 and more. Because it is coming closer to the cross-val score as well as your. Now, when you have like this, we need to print the matrix is equal to tree model dot predict classification report y comma tree predict. 0 1s are all. This is a balanced model. This is a very good balanced model. Overall accuracy is good and all the metrics are closer to one another. So this is a balanced model. Now from sklearn dot ROC display is there. Now what is the function for? So it is from sklearn dot metrics dot ROC curve display. ROC curve display dot from underscore estimator 3, x, y. So you got an area under the curve of 88. See 0.88. Good AOC. AOC is also very good. AOC is also very, very good. So all of you build the model decision tree classifier with depth of 10. Why reduce the depth? Because it was overfitting. How did I know? The cross validation score is very less. That gives us overfitting indication. How do we control? Using depth of the tree. No, if it is less than 0.50, AUC threshold is 0.50. The line that goes, if you look at the AUC curve display, the area is not given here. From here it is not there. That threshold is 0.50. The dotted line represents 0.50. Anything less than 0.50, we call it as an unsatisfactory model. 0.60 to 0.7 satisfactory, 7 to 8 is good, 0.80 to 0.9 is very good, 9 to 1 is, so our is in the very good category, 0.88. That this dotted line represents 0.50. Anything touching 0.50 less will be unsatisfactory model.
We need to change
Little bit of parameter variable adjustments have to be done. Hyperparameter tuning can be done or variable adjustment can be done. But generally we got very good one, 0.8 to 0.9. So it is not a problem for us. So you can look at this one, okay? I'm copying the image. See, there are metrics. It all depends on client which one metric he wants to take. He can choose based on accuracy. He can choose based on AOC. He can choose based on precision recall F1 score. It all depends on how knowledgeable your client is. Okay. And sometimes you do multi-metric comparison also. If you want to do a precise modeling, you do a multimetric comparison. AOC with precision, recall, and F1 score, and a ROC curve. The model which gives you all these parameters good will be your best fit. That is only for regression model. Regression also we have many: mean square error, mean absolute error, mean percentage error, mean absolute percentage error, RMS, root mean square error. All these things are there, but primary metric is mean square error. In time series, we look at all other metrics. MAP and MAE also, mean absolute error, mean absolute percent error. Same, that y hat minus y, only that part will change. People are done can build a random forest. Based on your RAM, if your RAM is around 8 GB, you can use 3000 trees because 12,000 observations are there. If your RAM is a problem, use less than 1000 trees. So next month, analytics with the hackathon, all of you must participate. Okay, next month around 15th or 20th, we will have analytics with the hackathon will be there, but all of you must participate. Now, because we have done majority of the important models which you can run there, so you can participate under the clear the MCQ test and then get the access to the data. We'll work on the data. Max depth only. Any tree-based model you want to control, it has to be max depth. N underscore estimators, comma, max depth 10. Whatever you have given depth in the decision tree, give the same depth. N underscore estimators, you give the number, comma, max underscore depth. Because in random forest, max underscore, see here, max depth is none. Max depth is none. Say nodes are expanded until all leaves are pure or until all leaves contain less than minimum sample splits. So you can want to control after N underscore estimators, you can give max depth. But cross validation, how much you got? Same 68 something, right? So random forest also give max depth of 10 with 3000 estimators. Any change in accuracy? Then it's good. Then it's good. That's not overfitting. See, actual accuracy to cross-val accuracy, 10% to 15% is okay. But beyond that, it's a problem. Even 10 also, 15 also is doubtful, 10% is acceptable. Plus or minus 10%. You also got one. Logic model one cannot have. You bring the graphs here when you encode in. That is when you have sorry, no, why is not the green graph? So when y is also there and this is also there, you get y. 88. 88. Okay, okay. And which one random forest? And underscore estimate. Okay, this is also better. But ROC curve. Classification important ROC curve will type, which is better model. Decision tree or random forest. All right, you can take your break. We will meet after 50 minutes. Okay.
Thirty-first we'll do it on online only. So some class will do online. Recording the video will go to it.
ఇచ్చే కదా
ఇచ్చారా
లాస్ట్ వీక్ కొద్దిగా బిజీగా ఉండే I was busy with my father. He has a back surgery on Saturday. So, multi-tree models, ensemble methods. Last time we talked about bagging, bootstrap aggregating, which is random forest. This time we are talking boosting method. Ensemble method, boosting method. The popular algorithm is gradient, also called as GBM. GBM is develop the accuracy or reduce the error of the model by focusing. Boosting means boost the wrong predictors. Wrong predictions are targeted. So these are developed to increase the accuracy of the model performance. They are purely developed to increase the accuracy. They perform slightly better than random forest. Not heavy change, marginally better than random forest. 1-2% or 5% change will be there. In terms of RMSE, plus or minus 100 will be there. The wrong predictors, wrong predictions, by adding weightage and passing them. So what it will do is it adds weightage to these wrong predictions and pass them through multiple. GBM uses sequential tree building. In random forest, what happens? Parallel tree building. Random forest is parallel tree building where each sample is independent. Parallelly, you can build multiple trees. Here, it is sequential. That means until tree 1 is built, you cannot build tree 2. Until tree 2 is built, you cannot build tree 3. So that is the sequential. Whereas in random forest, it is parallel because each sample is independent. Once the sampling is done, all the samples are independent. You can simultaneously parallelly build multiple trees, but that does not happen in boosting. It's an iterative algorithm. Same thing. Step 1, specify the number of trees to be built. Sample 1 by selecting 65% of rows, square root of number of build decision tree 1 per sample 1 and predict. Identify the wrong predictions and move them to sample 2, decision tree 2 and predict. Identify wrong predictions and move them to sample 3. So this process will continue till it builds that many trees. Sequential building of tree. Each tree is dependent on previous trees for sample. What sample? The wrong predictions or the misclassifications in the previous tree will be moved to the next sample. Decision tree 1 is built, sample for decision 2 will be created. Once sampling is done, decision 2 will be built. Then sample 3 will be created. Decision 3 will be built. Then sample 4 will be created and then decision 4 will be created. So one by one sequential building of trees. So if you are looking at decision tree is a single tree model, right? The single decision tree, no problem. Gradient boosting tree 1 will give to tree 2, tree 2 will go to tree 3, tree 4. Here parallel. Each tree is independent, right? There is no relationship between one tree and the other tree. Gradient boosting is sequential. Each tree is dependent on previous trees because each sample is independent. Parallel trees. This is single tree model. Now, if you are looking at random forest versus gradient boosting, in gradient boosting, trees are built additively. That means each tree is built one after the. So, and the main purpose is each new tree is built to improve the deficiencies of the. What is the deficiency? Wrong prediction. So each tree is built to overcome the deficiencies or wrong predictions in the previous trees. This concept is called boosting. Improve the previous tree. The primary job of boosting algorithm is improve the previous tree by adding weightages to the wrong predictions. Bagging is sampling method, purely sampling method. Bagging is dependent on sampling, randomized sampling method, where observations repeat in multiple samples and all. In bagging, the whole process is sampling. And if something goes wrong in sampling, trees will not be built. Once the sampling process is completed, then only the tree building will start, parallel building of trees. Multiple trees will be built based on your system's CPU cores. Whereas in boosting, each tree is dependent on previous tree. Until tree 1 is built, you cannot build a tree 2 because you don't know what was the problem in tree 1. And those problem observations are moved to tree 2, sample 2, then comes the tree 2. The whole thing is it tries to minimize the gradient or the loss function. Loss function means in accuracy, in classification problems, in regression problems, the loss function is RMS. In case of classification problems, the loss function is accuracy. True positive plus true negative divided by all 4 quadrants. In case of regression, root mean square error. Okay, so that is the objective. Here, the gradient boosting's main objective is minimize the deficiencies or the using multiple. So gradient boosting aggregates the results of each decision tree along the way to calculate the final result. Same thing, majority voting and average method. Final prediction is always based on majority voting and average method. The only thing is it is prone to, gradient boosting is again like decision tree prone to overfitting. You have to do parameter tuning. Now, gradient boosting is a very popular algorithm these days because there are variants. There are variants of gradient boosting that are there that will help you to increase the accuracies and win competitions. So, in random forest, we try to give more trees because that algorithm prefers. Whereas in boosting, it is opposite. Whereas in gradient boosting, it is so here. N estimators lower. You try to give less number of N estimators in boosting trees because a high number of trees can be computationally expensive. That is why we take few number of trees compared to random forest wants more trees. The more the number of trees, the higher the chance of more prediction. There also we can find the optimal number of trees by plotting the error plot. Where the error is becoming a straight line, we can cut off that line and then we can take it as it. In gradient boosting also, we have to give an estimators, but that should be as much as possible lesser than random forest, because gradient boosting works on a sequential basis and it requires lesser number of trees to bring the data to an accurate objective. So the number of estimators that you give in gradient boosting is comparatively lesser than random forest. Okay. And there are variants. So variants of which are popular are extreme gradient boosting, also called as XG boost. This is very popular. Light, this is also very popular in categorical gradient boosting, also called as CAT boost. So there are variants of gradient boosting like XG boost, light gradient boosting, CAT boosting. These are also very powerful algorithms, but they require little bit of computational power and hyperparameter tuning. Parameter tuning is very important from now onwards. These algorithms like neural networks, boosting machines, parameter tuning is very, very important. So the adjustment of weight, in what proportion you want to reduce the error, 0.1 or something like that. Right? So basically the thing you need to understand is the gradient descent algorithm. This is what is one of the combination of derivative calculus. The formula is this. Repeat until convergence, theta j is equal to theta j minus alpha. Alpha is a constant. Alpha into derivative of d by d theta j into j theta. So theta 0 comma theta 1 for j is equal to 1 and all. This is the important alpha. Alpha means a learning rate or the constant value, 0.1 or 0.0. Something you have to give in alpha or a learning rate. By default, I think in Python it is 0.01. Because the weight adjustments, like I told you, if you look at this diagram, this is the actual error we got. We are trying to minimize the error. Always minimize the error in smaller proportion. Don't try to reduce the error in larger quantities. Always reduce the error in smaller proportion over multiple iteration. And as you reach your error, the weight must be even. If you see here, the arrow size is decreasing, right? Gradient descent says you should reduce the error or you should minimize the error in smaller proportions over multiple iterations. If you try to do the error in large proportions, instead of reducing the error, it will jump onto this side and it will start pushing up so the error must be reduced in smaller proportions over multiple iterations. And as you reach your goal, the error must be smaller. One thing. Second thing, the error cannot be made 0. See, it is not touching the x-axis. There is always a minimum. We call it as local minimum. So you cannot make error. You have to maximize you have to minimize it to a not less than level. A minimization thing has to be applied. Now that value will be above 0. See that this line is not touching, right? So that means you can only minimize error to some extent only. After some point, the error will start increasing. So the point at which the error is minimizing, that will be your final error. And this error adjustment should be done in multiple iterations using a constant weight in a smaller. Now, yes, you have a doubt. It will jump to the other side and push the error. It will jump to the opposite side and then it will start increasing the error, which is against our objective, right? Now, you can see a small calculation also, this thing. So we have this data, age, square footage, location, and price. Some raw data is there, which is there. Calculate the average of target label. Target is price. So we calculated the average of target, which is 688. Calculate the residuals. Average of the weight minus this, you get the residual. 688 minus 480, you got the residuals, this one, right? So once you calculate the residuals, we calculate the decision tree. Square footage is highest. We'll take just take square footage as a value some tree has built using some residuals. Okay. And then he calculated the leaf values. Now see here, this is the alpha learning rate of 0. So he is correcting the predicted value from 688 to 654 point, and we will calculate the new residual, right? And he will build a new decision tree. He will be doing this process until he will get a point at which there is no further decrease in your error. So here the alpha is 0.1. A constant alpha is used to adjust. See the learning rate. You saw the formula, right? The weight adjustment is alpha. Now, if you look at your gradient boosting, it must be as much as closer to learning rate is 0.1. Now, you can see here, learning rate shrinks the contribution of each tree. This is a trade-off between learning rate. Values must be range between 0 to infinity. You can give any value from 0 to infinity. But a better performance, a value closer to 0 would be better. You want, you can give learning rate of 5, 10, infinity. But again, I told you, larger values will always, instead of reducing the error, it will jump to the other side and push up the error. So I'll play 0.1 to 0.5. 0.8. Like that, you can give different learning rates. Don't give learning rates in larger proportions, because instead of reducing the error, it will jump to the other side of the descent curve and it will start pushing up the. So by default, it is taking as 0.1 as the learning rate. Now you can give options 0.5, 0.8, 1, 2, 3. Like that, you can give. The value can be anything between 0 to, you cannot give negative learning rate. It has to be a positive value. So you can see, right, there is a lot of parameter tuning here. Here also you have max depth is by default is 3. By default max depth is, it's not none. In case of decision tree and random forest, it is. So you can see here, this is a little bit of advanced algorithm where learning rate plays an important role. Learning rate should be between 0 to 1, 0 to infinity. As smaller, better. You can give multiples of 0.1, 1, 2, 3, 4, up to 5 also we can give, but beyond that, it's a problem. If you give larger values, the error will not decrease, it will further. So the learning rate is a very important thing which you need to understand. See here, taking small incremental steps toward the solution achieves a comparable bias with lower overall variance. This thus prevent overfitting. Okay, smaller incremental steps. That means smaller incremental proportions. Smaller proportions should be your weight reduction. Again, we talk about this gradient descent in neural networks. How to adjust the weights using the same gradient descent algorithm. Always reduce the weights in smaller quantities over multiple. You give as many iterations as possible. That way your problem will be solved. No? You will at least reach a minimum goal. And minimum is always, minimum is not it local minima. It depends on the problem. There is always a local minima which is above. A lot of people think, can you make minima error 0? You cannot. You cannot make error 0. It can be, it will be above. A local minima is, which is acceptable. That is what we prefer. And gradient descent is a very powerful algorithm that is widely used. There are variants of gradient descent also. Stochastic gradient descent, adaptive momentum descent, ADAM. We call it as ADAM thing. So you have to understand the gradient descent, which is very important. It is based on derivative calculus. It is purely based on derivative calculus. Understood the word gradient in the gradient boosting? Reducing the weights in smaller proportion. Alpha. Repeat until convergence. Alpha into derivative of j by derivative theta j. For j is equal to 0 and k is equal to 1. This is the minimum cost that you can achieve. Sometimes it may stop before that also. Sometimes it may stop here only. We have to accept that. And we have to move the gradients. See, it is part inbuilt into the algorithm. The error, once it generates, it looks for the minimization, whether the minimization is possible or not. You remember solver, which we used in logistic regression. Excel, I told you, solver. Solver is a classical example where they were minimizing error, right? Where it randomly uses a different combination of values to reduce the error. So descent is similar to solver only, but slight different in the algorithm. That uses linear programming. The solver uses linear programming. Simplex method, dual simplex, all those things are there. Whereas this uses derivative calculus. Minimize the cost function using iteration. See here, the main objective is to minimize the cost function using the, no. This is a black box model. We can't do that. But if you want, you can manually calculate it. See, small running rate you can see like this. If it is large running rate, it starts jumping all over the place. You understood, right? What is the problem with large running rate? no stability will be there. It jumps from other side to other, sometimes it reduces, sometimes it increases. So you should always use a smaller running rate so that you can have iterations. You give as many as needed. Let the system take time, but you will have an error which is properly minimized rather than a large running rate where it keeps on jumping this side and that. It will never converge. Convergence means a minimum objective has been achieved. We use the word converge. Convergence means a minimum objective has been achieved. So types is this. See, batch gradient, stochastic gradient descent, mini batch descent. Adam is there, adaptive momentum. We use nowadays Adam mostly used is adaptive momentum, Adam gradient descent. So Adam moment optimization is also one of the method of gradient descent, which is widely used in image processing and advanced calculations in deep learning. You will see default as Adam. The default is Adam, like this. Calculate gradient, calculate PT, QT, PT hat, QT hat, update the parameters with this formula, return the weight. So this is a very advanced algorithm, which is the default in most of the deep learning algorithms. In the deep learning algorithms, by default, it will be Adam. So if you look at our gradient boosting, the loss is log loss, deviance, exponential, Friedman MSE squared error, where is the descent. So this is the theoretical background of gradient boosting. Exactly same like random forest. All other metrics, it gives you variable importance. It works with missing values. It works with any type of data. It works on large scale data. The only disadvantage is computing power. Like random forest, this also has a problem of computing power, but comparatively better performance than random forest. It's in boosting only. Boosting in neural networks. Wherever you need to do weight adjustment, wherever you need to adjust weights or coefficients. See, wherever we need to reduce the weights or coefficients to reduce the error, there you have a gradient descent. Yes, you can use the gradient descent version in logistic regression also, where we can do weight adjustment also. The coefficients, no? That's a very complex process. It is only used in academical studies. We don't use it in real time. But gradient can be adapted in any place where you are trying to adjust certain coefficients to minimize an error. There you can use gradient descent. I showed you, it will use the learning rate and then it will minimize. Last step, it aggregates all the predictions. Once the number of trees specified is ended, it will aggregate all the predictions and then use majority voting for classification, average for regression, and then it gives you all the remaining steps are same like random forest. The final step will be after all the trees are built, all the predictions will be taken, aggregated into one location, majority voting if it is classification, averaging if it is regression, and gives you the final prediction of the observation. It will be, that's what I told you, you can't make error zero. You can't make error zero. There will be wrong predictions all the time. In real-time data, it is very, see, if everybody behaves in a similar fashion, then you will not have an error. But do people behave in similar fashion? That means there is change in the behavior. So that's what I tell you now. You can't have people behaving in the same manner. Same education, same thing. Also, people will not behave same. If there is variation, there is always an error. That's what I'm telling you now. Error cannot be eliminated. Only minimization can be done. See, if everything is correct, why people default? Why do people who default still get loans? Why do people who default still get credit cards? Okay, one point of time, credit card default was 30%. Now, banks have developed algorithms where they have reduced it to 15%. That's they can do. That's all they can do. But I feel it's still 30% credit card default is there in India. Banks don't disclose it because of some technical issues. But then once you hit 30%, RBI says no issuing of new credit cards. That's all. You have to stop issuing. If they stop issuing credit cards, the whole department will be waste. So they have to show a number which is less, and then they have to issue cards constantly too. And credit cards is where they get more money, right? The interest is 36%. On a personal loan, how much they will get? 14%, max to max 18%. So instead of giving you a home loan for 3 lakhs, or personal loan for 3 lakhs, you give a credit card of 3 lakhs, you can make more money, no? So banks want to play the credit card game and they want to give that to as many people as possible. They want people to spend as much as possible. They want them to default on that or pay minimum amount to. Conversion to EMI, okay, they will get 18% or 17%, that's okay. But how many people will convert to EMI? They will default. Default means penalty, interest, everything comes into picture. Again, the collection guys will come into picture, and the ability of bank to collect will come into. If the ability is good, they will recover, and then they keep the money in there. That's what a lot of people ask me, why do with so much of risk give credit cards? Because higher the risk, higher the right. You get credit cards freely, right? You might get calls. Everybody calls. Give credit card, credit card. I only have saying no, no, no. Still, I have 6 cards. Despite saying no, 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 I have 6 cards with me. People spend wise, then it's okay. If people miscalculate or become into that debt trap, it becomes a very big problem, right? If you keep on paying minimum amount due, your interest will pile up and it becomes a big problem. Even if you convert to EMI 24%, you are saving some interest, right? Or even if you convert it to 18%, you are saving a lot of interest. So that is what happens. There will be error. In business, there will be problems. Now, your models will not eliminate those problems. It will try to minimize the problems and make your decisions what you call easy. So earlier loans were not given that freely, right? Because human beings were decided and people don't want to take risk. But now where is the loan coming from? Applications. Algorithms will decide. Algorithm will tell you whether to give loan or not. That's all. If algorithm says yes, loan will be dispatched. Bank will use the algorithms to give loans to people. But whereas when human beings are there, it depends on the purely bias of the manager. Even today, that's a problem for some public sector banks. They don't give loans, right? Whereas software is implemented and the algorithm says probability of default is less than 0.5, give him loan and credit card. If the probability of default is close to 1, don't give him any loan or credit card. Even if you are giving them, give it a smaller limit. A lot of people say, no, I got, you said 2 lakh credit card. Ultimately, it is approved for only 30,000 rupees, right? Or 25,000 rupees. Why? Because the algorithm has clearly told that there is a probability of default is higher. If the probability of default is higher, the credit card limit will be very, very. If your probability of default is less than 0.5%, whatever amount you are applying, you will get it on the card. So this all done by algorithms. That's why you can see the last 6 years or 7 years, the loan dispatching is very, very faster and this. Because human intervention is very, very limited. For every customer in the bank, a probability of default is calculated. And it is calculated every month based on your average balances, month-end balance, your EMIs, all these things will be taken and a probability of default will be. Similarly, the new thing, credit score. But credit score is updated every 3 months. Whereas your probability of default is calculated every month. At the beginning of the month, the probability of default will be generated for each customer for the loans and defaults. So they follow. Some people get calls for EMI, remember. Some people will never get. That means they're paying everything on. But if you missed one, next month onwards, they start calling you 10 days before, 7 days before, 3 days for 1 day before, all these calls will come, right? Reminder call, due date, all this, because you have defaulted one point of time, that is continuing. Your risk level has increased. If you are not getting any calls, you are paying your EMIs on time, they will issue more loans to you. More products will be given to you. That's what it is. So error cannot be eliminated. Please keep it in mind. It can only be reduced. And in some business problems, the errors will be higher, like in credit cards. The errors will be lower in home loans because home loan is a very long-term product and a lot of verification is done in home loan, right? So home loan approval is comparatively better than a credit card. So risk levels depend on the products in banking and insurance also same thing. Okay. So you have to understand the business problem and you should have an idea of the risk. And based on the risk, you should say, okay, I think I can only get you 0.7 or 0. Over the period, you will understand. By reading the business problem, you will say, I can get maximum 0.7 or 0.8 accuracy. I can't get more than that because the problem will be. So we always don't target 0.9 accuracy. A 0.7 or 0.8 also better for some problems. RT-PCR even today has sensitivity of 70%. What is sensitivity? Which is nothing but that's still there, 70%. So but we are still using RT-PCR as the basic, right? But because we don't have any other test. Because we don't have any other. If you are looking at that rapid antigen test, it is even horrible. Accuracy itself is 0.40. Rapid antigen, which you do it at home. That one, you have to put it and see the color and all. That has only accuracy of 0. It is less than 0.50. So which is better? RT-PCR is better, which is giving 70% accuracy. 30% misclassification. But what option we have? We don't have any other option. So we have to go with that one, RT-PCR. And RT-PCR is having less for the BS7 variant, the latest one, which is going in China and all, no? It is less than 70%. Recent studies have shown that it is between 0.6 to 0.7, the RT-PCR detection, because the test also needs to be updated as the virus. So you have to be careful. Based on the business problem, we need to adjust our accuracy levels. Textbook levels, very rarely we achieve in real-time data set. So it will be a range. 0.7 to 0.8 is a good number in business. I'm telling you in accuracy. In RMSE, something, if the units are in thousands, 100 to 150. If the units are in lakhs, 10,000 to 12,000 RMSE is better. Because we can't go beyond that. Okay. Any doubts in boosting? The other side of bagging. Okay. These are simply different testing. Here also random sampling. 65% of the thing, everything is same except the process of building the trees. Except the process of building the trees. The sampling is also same. 65% of randomly selected rows, square root of number of, and then you build the tree one, then find the wrong or misclassification, move to sample two. That is the only process. Everything else is same. Everything else is same. Tree sequential, until tree one is built, you will not have sample for tree two. Until tree one and two are completed, tree three cannot be done. So sequential, one by one you have to do it. But sampling majorly same, random sampling only it will use. And splitting methods are also Gini, and wherever there is a tree, there has to be a splitting method, right? And in machine learning, we use Gini and entropy. By default is always, okay. Because here in boosting, it is not worried about splitting methods and all. It is more worried about error reduction. So here learning rate becomes very critical. Learning rate and the number of trees is critical in gradient boosting. So from sklearn.ensemble gradient boosting classifier, GBM is equal to gradient boosting classifier, n underscore estimators is equal to GBM model is equal to GBM dot fit x comma GBM model dot score x comma y. Oh, 79.86. So we'll make it 3000. So I got with 1000 estimated 0.7986. Let us see if it increases. If I add more trees, see 0.84. It increased. Now let us look at the cross. Collaboratively, it will run faster. So 13 GB RAM now. 0.6865 something we got like this cross validation. GBM predict is equal to GBM model dot predict classification report y comma GBM predict. See, little bit better than random forest. Metrics are better than random forest. Similar to random forest only. Random forest was 0.92. But if you look at these metrics, see here 0.89, 0.71 and 0.79. If you look at that part, 85, 77, 81. So I think random forest would be a better option, but we can try increasing the trees in boosting again. We can try increasing the trees in boosting and see if we can come up with a better model. 5,000 trees. You can have max depth is by default 3, or you can add max depth is equal to 10. Like random forest, we give n estimators as 3,000 and max depth as 10. And then we can compare the similar parameter model. We can give that n estimators as 3,000, max depth is 10. Similar metric which we gave for random forest. The marginal difference is the 8.86 got. So predict classification report and then ROC curve 94. See, by making it 5,000 trees, our AOC increased to 0.94. This is a better model compared to random forest. Better model compared to random forest. 5,000 trees. Yeah, there is certain amount of overfitting is there, which is the problem I told you. GBM is prone to overfitting. But when you apply it on a new data, it has a better performance. It is prone to overfitting. That's what the theory guys are saying. But in decision tree, what happens is when you implement on test data, you'll get a drastically lower scores. But when you implement the same GBM model or a random forest on a test data, the model performance is stable. You can try it. You can try this model on the Kaggle competition thing. You remember Kaggle, we submitted decision tree. For linear regression 0.35, for decision tree we got 0.20. Now on the same Kaggle data, you build random forest and GBMs, you will go to 0.14 or 0.13. 139 will be a GBM score. Where right, it is performing like that. So these models are stable on production, repeated testing. Hello? Swiggy, third floor, reception వచ్చేసామ్మా. ఇదే బిల్డింగ్ లో ఉన్నావు కదా, ఇమాటికస్ లెర్నింగ్, HDFC బ్యాంక్ బిల్డింగ్ లోనే పైన. ట్రెండ్స్ వర్క్.
So now we are going to the
You go to the AUC. AUC and classification metrics. AUC and classification metrics are better.
the classification matrix will be
Zero. You have to focus on zero. Zero is the smaller thing, right? So if you look at the classification metrics here for zero, you got 0.87, 0.81 and 0.84 for zero. For random forest, 0.89, 0.71 and 0.70. Recall and F1 score are slightly that not good. But overall accuracy is again 0.84. Same. Accuracy is similar. But look at the minority class, random forest is having a problem. Now look at decision tree, all 79s. So decision tree to random forest, there is an improvement. Random forest to GBM, there is a improvement. If you look at logistic regression, see, from logistic regression to decision tree, it's an improvement. From decision tree to random forest, it's an improvement. From random forest to GBM, it's a improvement. So the hierarchy of model building has to be like this. If you build like this, it not only helps you to understand your data more, it also helps you to solving the problems. How do I increase the accuracy? How do I play with variables? All these things will be there. Now, logistic regressions give you by default not perform well, but still we have some understanding, right? We have a baseline understanding of our data, and then how much improvement we gained on decision tree, how much improvement can be made on random forest. But random forest to gradient boosting, marginal differentiation. Overall accuracy is 84. Within the matrix, there is a marginal difference. Marginal, not big difference. So that is how it will work. Tree-based models. They work with any type of data. Like you showed me that on that data, you build these three models, you will get good scores. Because your data is highly skewed, completely skewed. You can't correct it, right? So then what you have to do? You have to play with the tree-based models. Got it, all of you?
interviews like those data sets also like need to go.
Yes, you have to tell them, I have started out with the baseline model with this. I found out the problem with this accuracy was this and all compared to decision tree this. That's why I always put a table. You can scroll down to the GitHub and you can see the metrics on the table. I can explain easily for you, right? You do it in Excel. Copy these metrics and then you create the table. I showed you in the GitHub. I have sent you that GitHub link where I have given the template. Model, accuracy, precision, recall, F1 score, 0 and 1. And then you can compare them. Once you see the table, you will easily explain, right? So that should be your model. So we have developed this model. In Excel you have to do it, not in Python. See, that's what I tell in the last, in the what you call the Excel sheet, you have to create this format with model name and then the metrics, and then you do the comparison. See, this is the model. See, model accuracy, cross validation average, RMSE. This is a regression problem. Okay, model this is with log transformation, without log transformation. So built with normal, built with logarithmic. This is again based on what you call this is actual model without NLP. This is model with NLP. There is a text column which he deleted in this model. Before count vectorization means he deleted the text column that he deleted and he built the model. And if you look at all these metrics, which is better, gradient boosting is the better. So you see here, gradient boosting with n estimators has the highest accuracy compared to all other models. There is high impact of logarithmic transformation on RMSE, and the model accuracy has improved by 1.2% and the RMSE improved relatively after NLP. So before NLP, after NLP like this, you have to create a table, comparative table in Excel, and this will help you. So if you are looking at classification, here also there is this H1N1 prediction classification. This is a classification. See here, this is for seasonal vaccine, which is balanced data. So cross-val score, accuracy. For logistic regression, 0 and 1, the metrics and the ASC. Now, when you have data like this, it's very easy to explain and interpret. Template I don't have, but you can easily create. What is it? Oh, I'll create it and send it. Let me check.
So how do we know the bar?
This is seasonal vaccine. Both bars are almost closer. H1N1 vaccine. Look at the bar and this. Or you can do a pie chart also. If you're not comfortable with bars, do a pie chart. But bar is clearly visible. No? This is a H1N1 vaccine is imbalanced data. Look at the bar and look at this bar. Seasonal vaccine, the other dependent variable, they are closer to, they cannot be perfectly equal, but they are almost similar to, closer to one another. So this is a balanced data. This is your imbalanced data. Two dependent variables are there. Dependent variable only, no? there are two dependent variables, same independent variables. That's what now he has to build two different models. Two dependent variables means two separate models. See, this is the metric for seasonal vaccine as a dependent variable. This is for H1N1 as dependent variable. After doing the what you call, so you have to write your conclusion and all like this. So no problem. I'll give you this template next class, so you can use this for your version, or you can do Excel this thing only. So if you have these things ready, your explanation problem will be gone. You can look at the numbers and you can tell why which model is performing better. But avoid the diabetes, Titanic, Iris, and all those things. You please avoid. Textbook datasets, please avoid. Don't even think about them. Look at practical datasets which I am giving you. Competition datasets or datasets which are given by companies. Today's dataset is Amazon dataset, which they are used for Amazon research. So use this type of datasets, which will help us to. Textbook datasets, quotes are available everywhere. They will simply say you have copied from somewhere and all. But this in-vehicle recommendation and all, you will see very few notebooks. Hardly 10-15 notebooks you will find on in-vehicle recommendation. He was understanding the data, doing the process, comparative variables and all. It's a little bit complicated. So choose those data types which are absolutely real, like Medicare, seasonal one, H1 is also real-time data given by US Healthcare Department, driven data. That is also real-time data. Medicare data, which I am telling, it's a real-time data. Airbnb data sets, it's a real-time data. Trip predictions and all, which I think he's working on. That New York City, green taxi, yellow taxi data sets, they use them. That way recruiters will be very happy and you have handled the data, you have done the pre-processing, you have done the things properly, then only you can submit the model. I know people who stop in between because they can't go anywhere. But at least you guys will not stop in between. You know the methodology and process. You will have to build a model. That is what, if you follow the process, which I am explaining, you will definitely be able to build a model. Bringing your data to X and Y. That's all you have to do. A lot of people drop in between because they don't have proper understanding of the data. They get errors, they get confused, they get all these problems, they get stuck at point. But if you follow the methodology and process, which I am putting in the classroom repeatedly every time, you will not have you can handle any type of data. So we will stop it here and we will continue in the next session.